Hi folks, haven't posted a video in a while, but I'm back now. As expected, times got busy, real life happened, but things are back. So still been busy this week, so I haven't had a chance to make much progress on the game project. Hoping to get back to that soon. But I wanted to put together a quick presentation on something I've been thinking about for a while, which is how AI works, but without the maths. So I think that AI is perfectly understandable without any in-depth maths, and so I haven't really seen that in a video before. And also I want to talk a bit about why it suddenly got so huge a few years ago, and I haven't really seen that, and certainly haven't seen that put together with the technology and with the no maths approach. So I promise I won't use the words vector or embedding or matrix at all. Will not happen. If you can count, you know enough maths to follow this video. All you will need to know is that there is some maths that can do some things. You don't need to know how, why, or even what, really. So, what are we going to talk about? First, we're going to talk about what type of AI we're talking about, because that's kind of important. The terms have all got a bit conflated and fuzzy, so we'll define exactly what we're looking at. We'll have a brief history of language models, how we got to where we are today. We're going to talk about how we represent words as numbers. Again, no maths, so don't panic. Be fine. And then we'll talk about how machines learn. What is machine learning? How does it work? Because I don't think people necessarily have the best handle on this, and it really isn't that complicated when you get into it. And we'll talk about the relationships between words, which is hugely important and kind of key to the whole thing. After that, we'll talk about transformer models, which is what's really powered this latest explosion in AI technology. And finally, we'll talk about scale and how you scale these models and why that's important. So let's get started. So what AI are we talking about specifically? We're talking about large language models. So famous sentence, a quick brown fox jumps over the lazy dog. Everyone knows that, but the idea is given some words from a text, what is the most likely next word, and we want a program to solve that problem. And solving that problem turns out to be surprisingly useful. So this is how chatbots work. So if you build a piece of software that can predict the next word after a piece of text, and you give it as its examples lots of people asking questions and having them answered, then if you ask a question, it will think the most likely next words form an answer, and so you will get some question answering chatbot. If you give it lots of code, it will tend to output code. If you give it search, and you can, if you give it fragments of documents, it can look through them. That's another surprisingly useful thing. And even problem solving to an extent. So if you give it lots of examples of people journaling themselves solving a problem, then it will be able to journal how it would solve a problem, and obviously it depends on whether the problem is in its training set or something that it can get to from its training set. So there have been 4 real stages of language models. So the first was in the very early days of computing, handwritten language models. So programmers, computer scientists, linguists would get together, they'd work out rules for how language works, and they would write them down, write a computer program to process language according to those rules, and try to get it to perform some task. Now, language is not very susceptible to this kind of approach. So languages have millions to tens of millions to hundreds of millions of humans adapting them all the time, constantly, and making them fit their needs, and those needs are driven by hugely complex processes in the world. So there's lots of fuzziness, lots of ambiguity, lots of grey areas, and also humans are human. We make mistakes, we get things wrong, and then we adapt. So these handwritten rules were not very successful. They could be applied to solve some very specific cases, which is great, but it's really not a suitable approach. The next thing was something called a Markov model, which is a statistical model. Given these words, what's the most likely next word, based on a whole load of stats. that you have learned. And the idea was the machine was learning this. It wasn't handwritten rules anymore. And this was much more successful. And these actually had quite broad production applications, things like early translation models, early sentiment analysis, things like that. After that, we entered the era of recurrent neural networks, which we'll talk about a bit later. Now, RNNs initially were not as successful as Markov models, but eventually, as technology progressed, they caught up and overtook the Markov models for accuracy in a lot of regions. There were still areas where Markov models were better, but the RNNs eventually became the cutting-edge state of the art. And finally, transformers were invented, and transformers are the big thing we'll be talking about today. Transformers are what drive LLMs. They are the thing that caused the huge growth of AI as a subject in the world today. So, let's think about words as numbers. So, we want to process words, and computers are very good at numbers. So, realistically, we want to turn words into numbers, because that's the only way we're going to tackle this problem. So, we could just assign a random number to every single word in the sentence, like we've done here. That doesn't really give us a lot. It lets us store sentences fairly efficiently, and it lets us kind of write them into databases or something like that, but it doesn't really help us with language processing. But what if we try to give similar words similar numbers? So here blue and green are quite close together because they're both to do with colour, whereas hungry is completely different, and so we've given that a much different number, a very big number. Now, that's an interesting idea. That actually lets us use these numbers to know something about the words. But it has its own flaw. What would you assign full? Would full be close to hungry because it's to do with food and appetite and it's away from colour? Or would it be a long way from hungry because it's the opposite of hungry? It's very hard to figure out how to do that with a single number. So what if we don't? What if we give multiple numbers? Many numbers, in fact. So here we've given each 1, 2 numbers. So we've given blue and green numbers that are fairly close together in the first axis, and that's something to do with colour. We couldn't say exactly what, and these models generally aren't that understandable to humans. And then we've given hungry and full numbers which are quite far apart, but on a different number. So they're not in the first column anymore, they're in the second column, and hopefully you can see how that would help. So, what then if we give each word a whole bag of numbers? Instead of one number, give them a whole bag of numbers. And we have some maths. It's called a dot product, but you don't need to know that. You don't need to know how it works. All you need to know is that there's some maths that exists, and it can tell us how similar two bags of numbers are. And so then we can choose these bags of numbers so that words with similar meanings have similar bags of numbers, and words with different meanings have different bags of numbers. So how does this actually help us? Well, we'll get to that a bit later, but for now, knowing how similar two words are is probably quite useful if we want to be able to predict the next word. So I've got an example here where we've got the word car and the word petrol, and they each have a bag of numbers, and you can make a new bag of numbers out of the difference between those two words. And petrol is something you put in a car to make it go. And so then one can think about the words phone and electricity, and electricity is something you put in a phone to make it go. Phone and electricity also have bags, and we can take the difference of those bags and get another bag there. And it turns out that the bag for the difference between car and petrol, if we've built this properly, will be very similar to the bag for the difference between phone and electricity, and those bags will represent the idea of fuel or makes thing go or something like that. Again, we'll get into how we actually use these much later on, but for now, just assume that if we can figure out how to build these bags of numbers, they will be useful. So how can we build those? How do machines learn? So languages have tens to hundreds of thousands of words. We're going to want probably around 1,000 numbers per word in each bag. So you're talking about 100 million numbers. You couldn't possibly handpick those and tune them to achieve the effect we want. And this is exactly the kind of problem that machine learning is for. It's a problem where we know when we've got it right, we know what a good answer is, but we couldn't possibly build it ourselves because the work is beyond what any human or any team of humans could ever do in terms of time and feasibility. But sometimes machines can do them. How? How would we write a program to do that? Now, you don't need to be a programmer to understand this next bit. So let's introduce a box. So a box is another big group of numbers. And again, you don't need to know anything about how these boxes work. All you need to know is that a box is a big group of numbers, and if you put a bag into one side of the box, you get a different bag out the other side, and hopefully that different bag is related to the first one in some useful way. So let's say we write a very simple program where we have one bag of numbers per word and one big box for the whole program. And we want to put the bag from word 1 into the box, and the box will produce a new bag, and we want the new bag to be very similar to the bag for word 2. And remember, we have a piece of maths that will tell us how similar these two bags are, the generated bag and the word 2 bag. And then we repeat this for pairs of words 2 and 3, 3 and 4, all the way down as much text as we have. And the problem is we need to find what numbers go in all of those bags and what numbers go in the big box. And we need to do this by computer program, not by machine. So how can we do that? Roll a dice. Let's just pick every single number in all the bags and the box at random. It's completely random. Literally roll a dice. I mean, you probably can't roll dice that fast, so get the computer to digitally roll a dice. But that's it. Right? Roll dice, write down numbers. Well, the results will be terrible, right? The results will be completely random. But we'll know they're terrible because we can measure the result. We can measure how close the bags that are produced are to the bags we want. So what if we did this 1,000,000 times and picked the best one? Well, it'd be a lot better than just random. It would do much better than 50-50, but it still wouldn't be anywhere near good enough to be useful. But it's an interesting idea, and maybe we can expand on it. How could we expand on it? Okay, so what if instead of generating 1,000,000 random sets of numbers, we generated 10,000? And out of that we picked the best 100. And then we generated 100 random variations of each of the best ones. So you're tweaking the ones that are already good. And what if we then did that 100 times? So that 10,000 that we've just created by tweaking the original best 100, we test them, we pick the best 100, generate another 10,000 variations of the best 100 there. Do this 100 times. You will get a much better result if you do this. You will move your numbers gradually over time towards the numbers that give you the best answer. Even though you don't know what that answer is ahead, you know when you're moving towards it, and you keep picking the ones that are moving in the right direction over and over and over till you get somewhere near where you want to be. Could we do that even faster? Well, yes. Something called a genetic algorithm. This is one of the staples of machine learning for a very long time. Somewhat fallen out of favour now, sadly, but I'm going to mention it because it's not much more complicated than what we already talked about, and I have always been interested in them. I think they deserve a lot more attention and credit than they really get. So again, we'll start by generating 10,000 sets of numbers just by rolling dice, and we'll measure them all, and we'll pick the best 100. And then of those 100, we'll cut them into lots of little pieces. And the 10,000 new ones that we generate, well, we want to keep the best 100. But the 9,900 new ones that we generate, we will do so by reassembling those pieces at random and picking random pieces for the same slot from these best 100, and we'll repeat that 100 times, and this will get us even faster. This will converge, and this is used in lots of real machine learning problems. For a long time this was how various game systems were built. So I've done a little illustration here. So if you imagine we have two original best 2 out of the 10,000 or so, and each of them found one good answer. One found it there, one found it there, and now we cut it into these 4 segments. Now one of these 4 rearrangements will have the good one from the first, and then it'll just have to randomly mutate stuff until it finds more good answers. Another one will have a good answer from the second, and that will rank mid, and these 2 will rank somewhere around these, which was quite high, so that's fine. This one has none of the good answers, so that will rank terribly. But this one down here, by pure chance, has got both good answers from the 2 best, and this will outperform all of these by a very long way. So this is how genetic algorithms work. They aren't how we do language though. Language uses something called backpropagation, or at least the type of language models we're going to talk about does. So this is a different approach, and it's slightly less flexible. So a genetic algorithm can be applied to any problem that involves a big group of numbers. Just any problem that is defined by a large group of numbers you can use a genetic algorithm on, as long as you can measure the outcome. Backpropagation, you need a problem where bags of numbers get transformed into other bags of numbers by boxes of numbers. Sound familiar? Should hope so. So the idea is we have a bag of numbers and a box that produces a new bag, and a similarity test that tells us how similar the new bag is to the bag we wanted. But what this also tells us is how far away each number is from the number we wanted, and how far in what direction we would have to push it. And we can use this to work out exactly what numbers we needed to produce the answer we wanted in one go. Problem solved, right? Pick those numbers, job done. Well, I think you know it's not going to be that simple. So here's a problem. Words have many possible next words, right? Blue could be talking about someone who's sad, someone who's cold, it could be talking about music. And we can only process one next word at a time. So if we immediately move the word blue to be associated with the word sad, we would have a problem. But there is a bit of a get out here, which is that there are actually many possible combinations of numbers that can give us the answer we want. And the similarity test and pushing the errors back through the system only really shows us the easiest one to get to from where we are. So if instead of completely setting it to that, we just nudge it in the right direction, and then we have samples of other next words that nudge it towards where they would want it to be, over time it will gradually move towards an area that works for all of these words. It's when I say an area, the bag of words will gradually transform into one that works for all of these other words, which is what we want. So that's how we do it. So here's a problem then. I glossed over this a bit. I said we'll gradually nudge the bag of words to the bag of words towards the bag of words that we want. So the bag of words for blue will become what we want. What do we want? So I'm going to ask you a question here. Imagine you are the language model. You have been told that the current word is the word my. What's the next word? Can't figure it out? No, me neither. And that's because words alone don't carry the meanings that we need. What we need is context. So if I write I wore my, next word's likely to be hat, coat, watch, something like that. I drove my car, truck. audience mad with all these pauses? We still don't have an answer, but we've narrowed it down a lot. And the relationships between these words are what actually matters for understanding language. So how are we going to do that? Because our simple program that only took in one word and gave out an answer cannot understand the relationship between words. Well, what if we just made a really big bag of numbers, right? Like when I say it's a bag of numbers, it's literally a bag of numbers. So you could merge two bags of numbers together by just putting all the numbers from each of the bags into one big bag, right? Well, that's kind of reasonable, you could do that, but the box to process it becomes huge. Like, you would need more storage than could ever be created in the history of the universe. And the amount of training time would be impossible. It would be quintillions of years to train that model. You just couldn't do it. And by train, I mean give it examples, measure it, and nudge the numbers in the right direction. And it would take quintillions of years to nudge those numbers, because there's so many of them, and they would keep pushing each other in the wrong direction, and finding the exact right set out of such a huge thing would be impossible. Well, nothing's impossible over enough time, but yes, it would take an infeasible amount of time, let's say. So what else could we do? So, here's an observation. In the simple program, the bag of numbers doesn't output an exact match for word 2. It also contains some information about word 1, and it's just similar enough to word 2 to pick word 2. That isn't actually true. It produces something completely unrelated to the original bag, and we have maths to then turn it back into the predicted word, but we're going to gloss over that because it isn't really important for understanding. I'm just mentioning it so that I'm not misleading anyone. So, if we can output some of this extra information, if we can output information about word 1, could we use that to help word 2 predict word 3? Because now you wouldn't just have word 2, you would have word 2 in the context of word 1. So maybe we could output an extra bag with information about the earlier words. Something like this. Word 1 goes in, it produces a bag that tells us what word 2 is, and it produces a bag that tells us something about word 2 in the context of word 1. Word 2 goes in, word 2 goes in, as does the bag with the context, and word 3 comes out, as does a bag that tells us something about words 1 and 2 together in context. And 3, in fact. And then word 3 goes in, along with this context bag, and word 4 comes out. At least that's the theory. So there's a slight problem here which is to do with efficiency. So if you think about the phrase, say, his coat, that would have a very similar meaning at whatever point in, say, a book you're reading, right? And a book's likely to be, 100,000 words, something like that. So in the current approach, you would have to learn the meaning and what two bags to output for his coat for every single box, and there's one box per word throughout the system. And that's very inefficient. If you have 100,000 words, you have to learn that 100,000 times, when fundamentally it's the same thing over and over, that particular piece of knowledge. And remember, learning here is just tweaking random numbers until they do something useful. So what if we reuse the same box instead of having a new one for every position? Something like this. So if we take a word, put it into the box, get out the prediction of the next word and the contextual information, and then we put that contextual information back into the box along with the next word we want to predict, and repeat over the whole text. So now we have one box that's seeing the same things. So that's seeing all of the words. So the concept of his coat will only have to be learned once and can then be applied anywhere throughout the text. And this is what we do. This is called a recurrent neural network, which I mentioned at the start, and these turned out to be very successful. They were starting to approach the performance of the Markov models. I've glossed over the Markov models because they're not really related, other than they were the best thing we had before neural networks came along. So we still have a problem with this, which is each time the information passes through, it gets diluted. It has to go through this whole box of numbers that change and move it. And the longer it is since we saw a word, the more number of cycles through since we saw a word, the less influence that word can have over the context that we keep recycling around. And that's not the case for natural language. In a lot of sentences, words from further in the past are actually more important than more recent words. And this can span sentences, it can span huge amounts. Like if you think about Chekhov's gun, let's say, if a gun's shown on the wall in Act 1, it has to be fired in Act 3, so you would need to remember there's a gun on the wall in Act 1 for firing the gun in Act 3 to make sense. That's tens of thousands of words apart. So how can we deal with that? Well, we introduce a bypass that's controlled by the box, so we don't need to worry about how this works, but effectively the box can output some numbers that tell the system to store the current word or something about the current word for later usage, and then all of these bags that are from early words that have been stored as is get pushed back into the box every time unmodified, so you don't have this diluting effect on these. And then the box can also emit some numbers that tell the system to delete some of these bags. How does the box know what these are? Again, we measure whether it works or not, and we tweak it until it does. It doesn't actually know anything. We're just tweaking numbers. And this was called LSTM, or long short-term memory. And before transformers, this was the state of the art. It was much better than Markov models at text generation, which is the problem we're interested in. And it was a huge breakthrough, a big triumph, and was quite widely used. But it didn't take over the entire tech sector the way AI at the minute has, the way large language models did. So how did AI become the biggest story in tech? Enter the transformer. So large language models work with what's called a transformer model. And these arose from a slightly different field of language processing, which was automatic translation. And translating from one piece of text has slightly different requirements. So different languages have different word orders, so working across all words in a text at once was really important. And so approaches were developed to learn which words were important when. And one of these approaches turned out to be very, very useful for text generation as well. And that's the transformer, which we're going to talk about now. So let's restate the problem we have. We have a bag of numbers representing a word, and many bags representing the earlier words, and a box that turns one bag into another bag. And we want to mix together all of the previous bags, as in all of the bags from the previous word, and the bag of numbers that represents the current word, and turn that into a new bag. And remember, a bag, it's literally just a bag of numbers, just some numbers. That's all you need to know about it. And that new bag should in some way represent the meaning of the current word in the context and in relation to all of the earlier words. And some of those earlier words will have been important and some won't, and we need to figure that out. And then if we can do that, then we can have a box of numbers that has the ability to be pushed in the right direction, that it will be able to predict the next word accurately. So how do we build that new bag? So what if each word didn't have one bag? What if it had two bags? One of the bags is a group of numbers that represents the idea of what information I have, what I am. So I'm a colour, I'm a warm colour, I'm a cold colour, I'm etc. and the other says what information is relevant to me. So if I am a colour, what's relevant to me might be words like paint or pigment or not sure, that kind of thing. And so we can ask how similar the information an earlier word has is to the information that I want. And remember, we have a piece of maths that can compare how similar two bags are. And so then we say that if the information one of the previous words has is very similar to the information I would like, because I think it's relevant to my context, me as a word, me as the current word, that is, then if they're very similar, then we'll use a lot of that earlier bag in our new bag. And if they're not very similar, we won't use much of it at all. And we just repeat this over all of the previous words to create our new bag. And we can improve this slightly, actually. So, much like in the recurrent neural networks, lots of this relationship information is repeated across many groups of words. Think about the word is. Like, the word is says that something is something. You don't really need to learn that for every something and every other something. All you really need to learn it for is just the general case. So if instead of having 2 bags per word, we have 2 boxes that are global, as in we only have 2 boxes, not 2 per word, 2 in the entire system, and their job is to create the query bag and the key bag out of a single bag of the original word. And again, this is something that we can learn. We run the system, we see how good it is, and we nudge the numbers in the boxes until we get a good answer. And this is orders of magnitude less hard to learn, which means much better results in the same training time, which is what we're going for. And then there's a further improvement, which is not something you really need to care about, but I'm including it for completeness because the diagrams won't make sense otherwise. Neither the key nor the query bag are really very useful to mix into our new bag, and the original word isn't necessarily what you want to either, the original word bag. So we add a third shared box which turns the raw word bag into the actual value we want to add. So a new bag called the value that we want to add into this composite contextual bag we're creating. And that's basically it. So this is the whole system put together. So we have word 3, which is what we're trying to predict word 4 here. So word 3 is the current word. And words 1 and 2, they both run through these 3 boxes, produce a value, a query, and a key. These are bags, as you can see. Don't know why I said that. Important to note, these 3 boxes, and these 3 boxes are the same 3 boxes. But the diagram would look a horrible mess if I did it like that. So, we want to predict word 4 from word 3. So we get our query bag, again, just a bag of numbers, out of word 3. And we go to word 2, and we get its key bag, and we say, how similar are you? How similar are you to? And that produces what we call a weight. And that tells us how much of word 2's value bag to put into this new bag here. And then we do the same for word 1. We take the same query bag from word 3. This time we see how similar it is to the key bag from word 1. And that gives us a weight, and that tells us how much of the value bag of word 1 to put into this composite bag here. And if all of these numbers in these bags, 1 bag per word, and these 3 boxes in the whole system, if they've all done their job, if we've tweaked them until they're the correct numbers, this bag here will represent this word in the context of these other 2 words. So if this word is blue, and this is cold, and this is fingers, say, then this bag should represent the idea of having fingers so cold that they've gone blue. Put that into the box, the big box, and get word 4. And that is how an LLM works. That's how a transformer works. Now there's some details, some enhancements, so most of them don't just have one copy of this whole mechanism, they have multiple copies. So I was just talking here about the key here would be cold. But obviously blue can have multiple keys. It could have a key for music, it could have a key for query. It could have a query for music, it could have a query for temperature. And one of these mechanisms would represent temperature, one of them would represent music, one of them would represent sadness. And this is called multi-headed attention. You don't need to know that. But basically, you have multiple of these to produce multiple bags here. Which then, we use the same mechanism of the weights all combine across multiple of these to produce a single bag, that goes into this box. And then the other big thing is this is only one stage, and you would usually have, so this produces another bag out here. We had a bag going in, we've got a bag going out. There are similar pipelines for each of these words, so you have bag, bag, bag. And then what you would normally do, and what all of the big models do, is you take all this set of bags, chuck it into another set of this, and you do that tens of times. 30 seems to be about average. But it is all just this repeated. There's nothing new in any of that. So that's how transformers work. And they do work. We've seen they work. So why? Why have transformers taken over the world? You can see why this would be effective. You can understand, hopefully, from what I've just rambled on about for half an hour, why this works and how it works and what it's actually doing. But the question is, why is it so much more effective than LSTM was? What gives this its advantage? And that's a question of scale. So let's look at LSTM again, and let's say we've unrolled it. So we know there's only one box, but let's say each of these is a loop through the system. How would we make this faster? Well, the bottleneck is really that each word has to wait for the previous words to be finished before it can be processed. So you could try and make the maths faster, and we certainly do that. But in terms of this kind of maths, you're talking 10% every decade or so. That's not going to do the job if you want it to go 3, 4, 10 times faster. You could use a faster computer, but I assume if you care about performance, you're already using the fastest computer available, and clock speeds haven't been increasing that much for about a decade, 2 decades now. God, probably more. NetBurst was, what, 2000? Wow. But we don't really have anything much faster than that. Anywho. So that's LSTM. Making it fast is hard. What does a transformer look like under the same considerations? So here you see 3 words going through the transformer pipeline. And what you'll notice is there's only this one stage here where one word has to interact with other words. Not only that, this stage happens at the same point in time for every word. It's not dependent, it doesn't cascade the way the LSTM one did. So, if we want to make this faster, just buy more computers. Like, you could have the first word done by one computer, second word done by another computer, third word done by another computer. All the computers have to reach this point together, but they have to do roughly the same work to get to this point, so they will. And this is almost infinitely scalable. Now, you might be thinking, well, you only have 3 boxes in the whole system, and you only have 1 box here in the whole system, and they'd all have to wait to update that in turn. And yes, that's true. But that's only a tiny part of the maths, and also we have very good algorithms for batching this and for doing this quickly. Now, these aren't actually separate computers, they're GPUs that have separate pipelines, but you don't need to think about that, just consider them separate computers. And you can scale this almost indefinitely. So how much difference can this make? Well, you could have a processor per word, and a modern context is somewhere around 100,000 words. That means you can train at 100,000 times faster than you can something like LSTM that has to wait for each stage to update before it can do the next word. So an amount of training samples that would take 10,000 years to train on LSTM would take 1 month on a transformer if you bought 100,000 computers. Now 100,000 computers is expensive, but big tech has money. So why are these everywhere? Well, returns from tech had started to stall. SaaS had been put into everything where you could force people to subscribe and they wouldn't just walk away. Social media is largely saturated. We're not seeing the hardware improvements that sell phones anymore. So there's lots and lots of money that was floating around that was used to be seeing high growth return, and it wasn't seeing it. So it was looking for something that it could put money into and get a return out. And the previous model of big tech was largely to find a repeatable process and then throw money at it. If I can hire 10 salespeople, they run through this script, they sell this piece of software, I make X amount of money. If I hire 100 salespeople, they run the exact same process, I get 10x money. And then reinvest, scale, keep doing it. And so money in tech was looking for that opportunity. But it also needed something that would genuinely promise to improve efficiency, because, as we've said, tapped out with most of the ways of growing, so we needed something new. And so this technology comes along. It promises to do things quicker, more efficiently, and the only bottleneck is how much money you can throw at it. Throw more money at it, get better answers. And so the tech industry threw a lot of money at it. And they produced some astonishingly big models trained at unheard of scale that are genuinely miraculous. Like, these things are incredible. If you had tried to imagine what these things would be capable of and how long it would take to get here, I don't think anyone would have put it on this timeline. So, will this just keep scaling forever? Well, it's a good architecture, but it's not infinite. There are bottlenecks. So, previously, AI improved linearly with the amount of data that you threw at it, and it was limited really only by how much training time you could give it. And sort of the grandfather of AI, Geoffrey Hinton, he wrote an article about 10 years ago now called The Bitter Pill, where he was talking about way back when we had humans trying to write language rules for language systems. And it turns out that really what actually worked was just throwing more data at it. And this has worked since the 60s. The more data you throw at it, the better it gets, and it will outperform any human system eventually if you give it enough data. And for all of that time, the limit has been how long can you train it? How quickly, how efficiently can you train it? And the faster you can train it, the more data you can throw at it in the amount of time and money you have. But sooner or later, improving the training time will eventually mean that you have enough time and money to throw all of the world's data at it, because the world's data is a finite resource. And to an extent, it feels like we may have already reached that, because Transformers let us throw so much more data at these things than anything else we've had before, and that's why they're so successful. But there's a distinct possibility that they have shifted the bottleneck away from having the time to process the world's data to having enough data in the world. And even if they haven't reached that point yet, they will. If you keep scaling them, that will happen. Now, something else could happen first. It might be that there is enough data in the world that if we scale these models enough, which we may already have done, we reach a point where they are perfect. And by perfect I mean they produce the exact statistically correct next word every time for any text. Which brings us to a question. What proportion of problems that are interesting to the human race are solvable by a machine that predicts the next word? Now, like I said earlier, the ability to do things like reasoning by imitating someone writing a journal of thinking is incredible. Like, it really is. But I'm not convinced that this can solve all problems if you just give it enough power and enough processing. And then finally there's economics. The numbers of these things do not seem to add up at the minute. I could be wrong on that. I don't work at any of these companies. I don't know. But the numbers seem odd. And even if they do add up, there's no guarantee that things get better. It's well known that search is worse than it was 10 years ago, and social media is worse than it was 10 years ago. And in both cases it's because you can make more money by producing a worse product, because really the product is advertising. The product isn't the search or the social media, it's adverts. And so the user experience has gone backwards. And there's nothing to say that won't happen to these models either. This is all very pessimistic. They might keep improving forever, they might usher in a utopia. Would certainly be a good thing. But I'm not convinced. And that's all we have for today. So I hope that was interesting, and I hope it made sense, and I hope it was clear enough. I think I stuck to my promise not to use any maths, and I think I explained how the models work. You tell me. So until next time, as ever, thank you for listening, open to comments, and I'll see you next week.